So this is just first a disclaimer. The opinions that are expressed in my presentation are mine and may or may not reflect the views of the scientific expert panel that I'm a member of. They're not necessarily those of the Pacific Island Forum of Nations or any of its members. Okay, here we go. Does that work? Great. So at the beginning of the year, this year, the Pacific Island Forum of 18 nations assembled a group of 5 scientists to advise the Pacific Island Forum, or the PIF, on consultations with Japan regarding the discharge of wastewater into the Pacific Ocean. The presentations I've seen TEPCO give are very, very technical, so it's very hard to parse all the information. So in this presentation, there's a lot I could talk about, such as the legal implications, ecological implications, which are all very important, but it's outside my expertise. So I'm not going to touch on it too much. And this is why the PIF Secretariat has assembled this amazing group where everyone has different expertise. It's a true honor to actually work with all of them. They're all amazing scientists. What I will also not discuss, which is my concern, is that the dumping of the contaminated water over 40+ years will deeply affect the fishing industry in Japan and neighboring countries. The fact that the fisheries industry will suffer reputational damage, which is tragic, but that's beyond our mandate. That's not what I'm going to be discussing. Rather, I will focus primarily on what we will have learned from the radionuclide data that TEPCO has shared with the PIF Secretariat, and which is kind of my role in this group of scientists, and other documentation that TEPCO Japan has published. We've had 4 meetings with TEPCO and the Japanese government officials over the year. The IEA was an observer in one of the meetings, and it was great that the IEA Director General Grossi met in person the PIF members in Suva this summer to discuss the issue and describe the IEA's role. Some members of our scientific panel, me included, were virtual observers at that meeting, yes. So as the PIF Secretary General Henry Puna has said, our ultimate goal is to safeguard the Blue Pacific, our ocean, our environment, and our peoples from any further nuclear contamination. This is the legacy we must leave for our children. I don't need to remind you all, right, that it was in the Republic of Marshall Islands where the nuclear tests have occurred. So they have a lot of legacy when it comes to nuclear materials. I will discuss our findings and conclude with our recommendations. So first, bottom line upfront, very Washington, D.C., BLUF. Bottom line upfront, Japan TEPCO plans to discharge 1.3 million tons or meters cubed of contaminated water into the Pacific Ocean over a period of about 40 years. The water itself is contaminated and will be diluted at least 100 times. That's what TEPCO says. TEPCO keeps on emphasizing 100 times, but the reality is that I've seen measurements that require dilution, is really with regards to tritium in the water, that require dilution of at least 1,500 times. So the 100 is just a placeholder, let's say. The stated standard will be no more than 22 terabecquerels tritium per year. So terabecquerels 10 to the 12, so 10, with 12 zeros. Becquerel tritium per year. So becquerel is decay per second. I'll discuss that a little bit later. And with a maximum concentration of 1,500 becquerels per liter. Of course, there are many other isotopes other than tritium in the water. And this is what I really want to bring home in this presentation. And TEPCO has stated that the sum of the radioactivity of 62 isotopes divided by their legal limits should be less than 1. This is the figure of merit that they use to decide on whether the water is fit for disposal. The approach has been used in the past. That is, dilution is a solution to pollution. It's kind of a common phrase that people use. But this underestimates some of our other concerns. We oppose this on a scientific basis and recommend an alternative approach. It's time for new thinking and for Japan really to lead in this, because there has been dumping of tritiated water by many other reactors. I'm going to discuss that a little bit later. Countries like South Korea and Japan, the countries that have been, not Japan, China, that have been most critical of this method, have dumped dump discharge tritiated water every year. So it's important to keep that in mind. I will discuss that a little bit later. So it's time for new thinking. So introduction to the problem. I think, Masako, you framed it perfectly, so I won't go into too much detail here. So we wrote an op-ed in August in the Japan Times, but what I want to do in this presentation is that we have some time. I want to take this opportunity to describe our thinking in more detail. You can kind of think of this as the presentation as the annex to the op-ed. It's a little bit technical. That's because we want to get into the details and discuss our concern, and I hope you'll allow me to do that. So Masako already said this to some extent, but more than a decade ago, I can't believe it's more than a decade ago, 3 reactors melted and the top of a 4th exploded in Fukushima, Japan, after a devastating earthquake that occurred. It was the worst nuclear accident that we know of since Chernobyl. More than 100,000 people were evacuated. There were at least 2313 disaster-related deaths, not from radioactivity, just to be clear, among evacuees from Fukushima Prefecture. And it's in addition to about 19,500 that were killed because of the earthquake, terrible earthquake that happened, or the tsunami. And as Masako already said, 30,000 people can't return to their homes even this day, more than a decade afterwards. The 3 cores themselves contain a vast amount of radioactive material, and only a few % of it actually escaped into the Pacific Ocean. The rest remains in the reactor itself. I want to apologize a little bit for all the AI-generated images. I've become very excited about just putting a text in and generating all these images. So some of these pictures may not be so relevant. So as of November 24th, last week, from the real-time plant data, where I have the reference there, you can look up yourself, there's about the pressure vessels themselves are still being cooled, requiring about 6 meters cubed per hour, or over 1,000 meter cubed per week. It's an enormous amount of water. Rainwater and groundwater has also been flowing into the reactor complex from nearby mountains, and the water becomes highly contaminated with radionuclides. It picks up from flowing through the reactors themselves to the buildings and so on. In 2016, TEPCO admitted what many of us suspected, that the water is not being stopped by a much hyped ice wall that they discussed. Again, happened in 2018, 2020, and 2022. And the references are there as well. And groundwater is important, is made worse during the rain season, especially during typhoons and so on. Now, TEPCO has no plan to completely stop the flow of groundwater. This is such a tough problem. Instead, it continues to deal with the problem by putting contaminated water in tanks, and there are so many of these tanks. This just kind of shows you the water burden that they have to deal with. This is a trace that I did of a very busy TEPCO graph that's not suitable for presentations because it's just too much in it. So I hope you excuse a little bit artistic license of how I traced it. But here you can see the changes in the groundwater throughout the year. The volume is highly correlated with rainfall that you see at the top. And you can see that the groundwater flowing into the heavily contaminated reactor and turbine building ranges from about 100 to 1,200 meters cubed per day. This is a meter cube means 1 meter, a cube of 1 meter. So this is an enormous amount of water to deal with. It's mostly around 180 meters cubed per day. At the high end of 1,200 meters cubed per day, that's about 1/2 the size of an Olympic swimming pool. It's an enormous amount. And TEPCO has a difficult challenge to deal with to manage so much water and has placed them into tanks. So talking about Japan's mitigation measures, here you can see the tanks, right, or some of the tanks. According to TEPCO, there are over 1,066 tanks holding contaminated water. To visualize how much water this is, it's equivalent to a total volume of a cube of water that's 110 meters on each side. Almost 1,000 Olympic-sized swimming pools. It gives you a sense of how much water, contaminated water is to deal with, what a difficult problem it is. So the water coming out of the tanks is highly contaminated. The water is treated to remove 62 different radionuclides using a system known as ALPS, which is a multi-nuclide removal facility. In 2014, TEPCO stated that ALPS, this is a quote from them, ALPS will reduce strontium to non-detectable or ND levels, which will reduce the risk of leakage and protect the safety of workers. So that was back in 2014. In August 2018, Kyoto News learned that TEPCO ALPS system was not working properly. You can see the links there. Kyoto News revealed that the water was still highly contaminated. And then later, TEPCO admitted that about 66% of the treated, it's the number now, at that time it was 70-something%, of the treated water needs to be treated again because the water still has high concentration of radionuclides, resulting in a figure of merit, which is often much greater than 1. So just to tell you, so here, here is this figure of merit that I have. It's the one equation that I have in the whole presentation. It shows you the this sigma, which is shorthand for mathematical for sum of. So it's the sum of the contribution of the 62 different isotopes, different radionuclides, of the concentration divided by what is legally allowable. And that number, as a figure of merit or level of risk, needs to be less than 1. Okay, so that's what TEPCO has decided is it's important before release. So let's call this TEPCO's figure of merit. It's one way of accounting for the contribution from all 62 radionuclides and as a kind of quantitative risk factor. Note that tritium and carbon are not included. That's why I say 62, not 64. Right? Tritium and carbon are not included because their numbers are so high. Especially tritium. It's not, let's be a little bit careful here. Tritium and carbon cannot be removed with the ALPS system. Okay. And TEPCO plans on diluting them. But the total quantity of both will be discharged into the sea. So if you think about the total quantity of what's sitting in those reactors, if the water has picked it up, that will go into the sea. It's just will be diluted. Okay, great. So let's talk about the problem with the ALPS system. In the top panel, you see the distribution of the initial ALPS system. So this was before some of the changes that have happened recently to the filtration system. And it shows the fraction that cannot be released, grouped according to the risk factor or the figure of merit for release. Remember, 1 is what's allowed. If it's 2, it's not allowed, right? So it's twice the risk factor. So in this case, about 60% of the 1.3 million meters cubed of ALPS treated water cannot be released, initially treated, and needs to be retreated. 18%, or 1/5, essentially 1/5 of the water, has a FOM risk factor of more than 100, right? Some as high as 20,000. So in other words, the figure of merit was 20,000 times more than what is allowed of some of the water. TEPCO uses the word secondary treatment, but in actuality, I prefer to use the word retreated because secondary makes it seem, because I don't like the word second, as if it only has to go through the system once. I think it would probably, depending on what you're looking at, it could be much worse. And then the wide variation in the figure of merit of the ALPS treated water is also consistent with the data that we analyzed that was provided to the PIF Secretariat by TEPCO. The bottom panel shows in red the strontium-90 measurement. So strontium-90 is a very important isotope. It's a bone seeker, as they say. It acts like calcium. So in red, it shows you the strontium-90 measurements if the ALPS treated water of the data set. So the data set that I got and analyzed is large, and I only analyzed focus on the ALPS treated water. And the black dots are the lowest concentration that can be determined with the instruments used and the protocol followed. So the measurements, so in this case, those measurements were only lower limits that could be set from the samples. So if dedicated experiments are not done with tracers of those radionuclides of the same chemical form, then it's impossible to know how well the ALPS treatment works for the different isotopes. Also, the limits of detection for the same isotope also varied greatly across the data set, as you can see in black, for strontium-90, which I don't really understand why there would be such a large variation. Maybe because there was a background measurements around where the strontium peaks would be, but I don't really understand why there was such a large variation in the background using assume the same detectors that were used. So this shows the operation time of the ALPS system. This figure It's actually data pulled from archive.org Wayback Machine, because what happened is TEPCO used to publish this on their main website, and then the first page is always what's backed up on the Wayback Machine, but now it's secondary and third weight pages, so it's much harder to extract. And so what we see is that since late 2021, there has been little change in retreating the water. So I'm not sure what the reason is why they're not doing more actively retreatment of water. TEPCO has poor knowledge of source terms, which creates great uncertainty about how many times the water would be run through the ALPS system. As you can see, it seems like there was some pilot studies that were done, but I think there's still uncertainty about what's actually happening here. It's that similar AI image, just not really appropriate, but it's there. What's in the water? So Japan's focus has really been on tritium in terms of dispersal and dilution. But we've analyzed the data provided by TEPCO to the PIF, and I've come to the conclusion that too little is known about the water to really allow disposal. And in what follows, I will discuss what we learned from analyzing the data itself. So just before the incident, the reactor itself was very radioactive, which is measured in terms of the number of decays per second, or becquerels, that I already discussed. The number of becquerels can be directly linked to the amount of material of a particular radionuclide. As you can see, the radioactivity was enormous when the reactors melted. And at the high end, the core contained as much as 700 petabecquerels, so that's 10 to the 15th, cesium-137, and 520 petabecquerel of strontium-90. So one petabecquerel is equivalent to 1,000 raised to the power of 5 decays per second, right? And so, as I always say to my students, you can think of a decay per second as essentially a bullet that's flying off, a radioactive, just a particle that flies off, and that's what does the damage to DNA and to the body. And so this is an awful lot of bullets that would be flying in different directions. So as an example, let's look at cesium-137, which has a long, I didn't talk about this, strontium-90 also has about a 30-year half-life. So cesium-137 also has a very long half-life. And it's present at the reactor at 700 petabecquerels. So during the incident, cesium-137 has been estimated to be released in the atmosphere at 15 petabecquerels. That's 2% of what's in the core. So that's an estimation that they did. You can see the reference there, it's reference 1. At a regular, and then the cesium-137 was released into stagnant water in reactors, which was 10 times higher than what was released into the atmosphere at about 20%. So 2% versus 20% of what's in the core. A regular US BWR on average releases about 1 million becquerel per year. So these numbers are really very, very high. To put this into perspective, the amount released into the atmosphere was equivalent to the release of cesium-137 of a regular BWR reactor running for 10 billion years. That puts a different spin on how serious it is. These numbers are huge, and if the water picks up even a fraction of the strontium-90 or the cesium, it will be a very high load for ALPS to process. You can see all the references there that I have, and I'll circulate the presentation so that you can follow up and see how I got these numbers and things like that. So TEPCO's data set of measurements. So first of all, measuring the quantity of radionuclides of the water in the tanks and the water before discharge is critically important in order to understand the concentration of radionuclides in the water, right? TEPCO measures the radioactivity of the water using a variety of tools such as ICP-MS, induced coupled plasma mass spectrometry, and various beta and gamma spectrometers, also liquid scintillators, and so on. And these detectors can simultaneously identify the radionuclide present and assess how much of it is present by just counting how many particles you detect. However, they depend on proper procedure and quality control and being able to assess the lower limit of detection of radionuclides, the level above the background noise. So in this section, I will critically analyze TEPCO's data that they shared with us. So there have been, first of all, a very small number of measurements. So here I kind of want to summarize our concerns because I'm going to get into a little bit more detail So there's been a small number of measurements over 4.3 years that cover the data set that we have. and a small number of radionuclides have been measured per sample. TEPCO continuously focuses on the primary 7 radionuclides, which underestimate the risks due to all the other radionuclides. There's been also a large variation in the concentrations of the radionuclides and the ratios between radionuclides, which is concerning. And TEPCO's method of taking samples introduces bias and assigning a value for 55 isotopes for the release figure of merit that are not actually measured, just a number, is also problematic. And there's also questionable data, which are likely due to poor data quality and procedure. So first, this graph here. And so what this is showing you is over the 4.3 years, all the number of measurements that were actually made, which I think is, to be honest, pretty pitiful. I think there should be way more measurements made than what we have here. So we requested data for all the 62 different radionuclides. 54 days later, we received 19 data files containing the sampling data that covered 4.3 years. The data needed extensive cleaning and had large gaps in the data. There was no mention of mixing and hardly any mention of attention to sludge in the tanks. Tanks are often not remeasured, so temporal variation is very hard to know. And there's relevant data is missing from the sample as important as the tank ID in some of the data sets that I've seen. And at times it makes it difficult to figure out how broadly the 100 tanks were sampled. So tank measurements have focused on only about 7 out of 62 nuclides that should have been tested. Tritium and carbon also not tested that often. And TEPCO calls these the primary isotopes. The 7 isotopes are strontium-90, which are the bone seeker. As I said, it's very, very important. Cesium-134, Cesium-137, the one that had the 30-year half-life, iodine-129, ruthenium-106, antimony-125, and cobalt-60, as you all know, a very important isotope. And you can see in the chart that at most 19 radionuclides were measured per sample. In almost all cases, only 7 or 9 radionuclides were measured, and not once were all 62 radionuclides measured in one sample in all the data that we analyzed. So the data set focused primarily on 10 radionuclides, TEPCO 7 plus tritium plus technetium-99 and carbon-14. On average, about 7.5% of all 64 radionuclides were directly measured over the data set, which is, it's a key criterion for the public that all 64, that's what TEPCO promised, that all 64 radionuclides would be measured, the concentration. So what I say is, when I mean 7.5% of all 64 radionuclides, what I mean that 100% would be if 74 isotopes were measured for every sample over the complete data set. 38 isotopes of the 64 isotopes were not measured at all during the 4.3-year data set, including plutonium and other important isotopes. There's large variation in the radionuclide concentration of isotopes in the tanks and the ALPS treated water. Here we see the ratio of strontium-90 to cesium-137 as an example. You can see that there's large variation in these numbers. It's very hard to understand the concentration in these tanks. You really have to understand the history of where this water is coming from. But it may also have to do with problems with the ALPS system, which I also want to discuss. Note that I've plotted the measurements organized from high to low. Okay, so it's not like this is, I've actually organized it this way. Which is why you have this shape. And we see that the strontium-90 cesium-137 ratio in individual tanks varies by a factor of more than 8,000 in at least one case. So this indicates variability in the ALPS system, not just in the overall efficiency of the total radionuclide removal, but variability over time in the ability to remove individual radionuclides at a constant efficiency relative to each other. And in this image, it shows the maximum value and the median value of this FOM risk factor, the figure of merit risk factor, for radionuclides that were measured in TEPCO provided data set. Recall that the figure of merit greater than 1 for any isotope does not allow disposal. This is TEPCO's own criterion. And you see that it's only a handful of the 62 isotopes. There were wide fluctuations in the values for the same isotope throughout the data set. And note that critical isotopes like plutonium were not measured, as I mentioned before. TEPCO has focused on the 7 primary nuclides, but when all radionuclides are taken into account, including tritium and carbon-14, we see that the figure of merit is much higher. Again, I'm always showing these logarithmic scales that go up by factors of 10, right? This is not a linear scale. It's really important that TEPCO really measures all of the radionuclides, not just 7 and infers the rest. So let's talk about a little bit about inference. So an additional concern is how samples were taken for analysis. TEPCO takes 30-liter samples at the end when a tank is being filled. By not taking samples randomly, it's unclear how representative the samples are of the content in the tank. Rather than measuring all 62 radionuclides as the public has been led to believe, TEPCO only measures the 7. And as described in the radiological impact assessment, which was released in November 2021, if I'm correct, and then another release in April, and kind of updated that in July or April of this year. And as described in the RIA, it simply assigns a 0.3 for the FOM for the 55 radionuclides that are not measured for the ALPS treated data set. So that means that those 55 radionuclides are not actually measured. It's just a number is assigned to it. So although the original document is in Japanese, it's called the ALPS subcommittee report number 10, reference number 2, doesn't mention where the samples were taken. I believe the samples were taken from only one tank group, and it's not sure whether the tank was mixed, agitated, or not. In a similar way, the presence of carbon-14 is not measured, but it is assigned a value of 0.11 to this FOM risk factor. I identified a particular measurement that TEPCO provided in the data set that had this value, 0.11. But what you can see here in the graph is that you get a large variation in what carbon-14 is across the tanks. This was across 80 tanks that they measured. And Houston, you don't know whether this could fluctuate higher or lower or whatever. So I think it's problematic just to associate one number and not measure it. So it's always possible for this to fluctuate up. So the late release of the RIA, which was in November 2021, also it's not, by the way, an environmental impact assessment. It really should be done. It's a radiological impact assessment. And many people have criticized the RIA itself. It does not really give the public much time to challenge if it's November 2021, and if the release is supposed to happen in the spring 2023, it doesn't really give much time for the public to really react to all this because it's so soon that this discharge will happen. So there are also a number of anomalous and questionable data points and measurements in the data set provided to the PIF by TEPCO. For instance, in the insert, you can see very high lower limits on the radionuclide tellurium-127, which simply should not be present. It's got a 9-hour half-life, so it should not be present. It's a fission product, so it should not even be present. A decade after the incident happened. So it shows a lower limit, which means a limit of detection, lower limit of detection of 4 million times of what is legally allowable. So what does that mean? So I'm not sure why tellurium-127 is recorded with such a high lower limit of detection. I did try to figure out why this is so hard. It seemed to me, I talked to some other, because I come from a whole detector background. There's a 1% gamma ray, which is, so it occurs 1% of the time with, I think, 400 kilo electron volts, which is far above the background for a high purity germanium detector. So in my opinion, they should have detected that. So I don't really understand, and I'm trying to figure that out in more detail. And so most likely though, the tellurium-127 lower limits, it doesn't, I don't think there's criticalities going on or something like this, but I think it just indicates that TEPCO's measurement and quality control and procedures are poor. We did confront TEPCO about these measurements, and they didn't really give a satisfactory answer, at least not from my take. Other concerns. So maybe preface this with IEA is an incredible organization. The work that they're doing in Zaporizhia is just incredible, all the effort that they're doing. When I looked critically at the data, I'm looking at it from a scientific perspective and reading IEA documents and so on. So it by no means means any critical of the IEA in terms of all the incredible work that they're doing. But I'm going to talk about the IEA support and involvement. The IEA has been involved in reviewing Japan's discharge plan since the first terms of reference was a signing ceremony, which you see here in July 2021. The terms of reference were signed by Deputy Director General Dedi Evrard, who heads the IEA Department of Nuclear Safety and Security, and Ambassador Takeshi Hikihara, Japan's permanent representative to international organizations in Vienna. So the IEA assembled a task force to evaluate safety elements of the discharge plan and has issued 2 reports, and a third one is expected to be issued this month or so, at least very soon. And we've evaluated these reports by the IEA. We are concerned, given past failures with the ALPS system, about the ability for ALPS to handle the large volume of water. The data I've seen for the new version of ALPS does look promising for strontium, less so for cesium-137. And it does not filter carbon-14, but it was done with only 0.07% of the full volume, and hence it's not really a representative sample. We also have questions about how the samples were taken and so on. So a plan for concentration measurements of all 62 radionuclides was described. It's on page 186 of April 2022 revision of the RIA, Radiological Impact Assessment. But given that, for example, plutonium isotopes have rarely been measured, TEPCO needs to demonstrate that they can do that they can actually do these measurements for a high throughput and a high turnover rate of samples. Given that the discharge is supposed to occur in spring, summer 2023, we are concerned that the IEA has not requested TEPCO to demonstrate their ability to measure many of these radionuclides. We're not convinced that given the issues with sludge, etc., and little measurements, that TEPCO knows with high confidence what is actually in the tanks. We're also concerned by IEA's lack of interest for what is actually in the tanks now. Their stated main concern to the PIF members was not what is in the tanks now, but what is the situation after ALPS. In effect, the IEA has endorsed the discharge plan without adequate knowledge of radionuclide content of the tanks or of the ability of the ALPS system to handle the actual radionuclide load. So in July, Japan's NRA, the Nuclear Regulatory Authority, authorized construction of the equipment to permit the discharge. That occurred in July. In September, TEPCO allowed the public to see the construction, which is pictured here from Stars and Stripes newspaper, of the 1 kilometer pipe, because that's going to be a 1 kilometer long pipe, and this is about 8 meters, is already complete. So the public was allowed to watch. This clearly demonstrates that TEPCO wants to continue with this process and is basically putting their foot down. At least that's how I see it. Our opinion is that to prepare for discharge before doing the necessary sampling to establish tank contents of all radionuclides is premature. The source term needs to be established much better than it has been. The ability of the ALPS system to handle the varied contents of the tanks, including early tanks with particulate loads and sludges that may be stirred up as the tanks are being emptied, has not been satisfactorily established. Waiting until the time of discharge to do full and proper sampling is not appropriate from a scientific or ecological point of view. One of us, Dr. Boosler, mentioned in his November 2021 comments on the TEPCO radiological impact assessment that RIA does not mention at all organically bound tritium, or OBT. This is not an area of my expertise, and Thankfully, Dr. Arjun Makajani is online. He can answer questions if you have those afterwards. But OBT or forms of tritium can come in many different forms in terms of how they bind to the body. And generally, TEPCO has emphasized that it basically is just like water. But that's not necessarily how tritium behaves. Tritium binds to organic molecules and so on inside the body, a certain percentage of the tritium. And we discussed this issue with TEPCO during our June 2022 meeting at that time. And TEPCO informed the expert panel that TEPCO is basing its values on the standards associated with drinking water. However, using drinking water conversion factor is not appropriate, since the water will not be consumed by people. The parameter of interest, therefore, is not what happens in the human body when tritiated water is consumed directly, but what happens in oceanic ecosystems. Background concentrations of tritium in seawater are a fraction of a becquerel per liter. And we're talking about putting in 1,500 becquerel per liter. The proposed discharge concentration is then thousands of times natural and nuclear testing background concentration. So there are many different geochemical forms of OBT, and each have, I can discuss this here, have a different fate in the ocean. So unlike for tritiated water, HTO, it's not H2O, but HTO, the environmental quantification behavior, OBT, are not well understood. And TEPCO's preparations did not discuss complex ecosystem issues and therefore is inadequate. Because of the complexity of the ecosystem, we can't be assured that the harm will be minimal. And we recognize that much regulation is still based on the idea of dilution is the solution to pollution, right? However, the science of protecting the oceans and its ecosystems, including but not only the human beings who depend on the oceans, has moved far beyond that notion. And we're also aware that the discharge of tritiated water is routinely done by BWRs and PWRs and reprocessing plants. And as I've said, even done by countries that harshly criticize Japan, such as South Korea and China. However, as Dr. Busler has pointed out to TEPCO, the total amount of tritium to be released is greater than estimates of tritium released in 2011, which was 0.1 to 0.5 petabecquerels. So this is not standard operations, right? But a deliberate release that's on the same scale as the 2011 incident. And ocean dumping is still dumping. So conclusions and recommendations. So discharge in the ocean is cheaper than alternatives and solves the problem within 40 years, which is the goal. There was a plan that TEPCO in Japan have put out, which was a medium long-term plan to solve the whole problem in 40 years and be done with it. But it's not as simple as that. There are a lot of problems with removing the fuel and issues related to the water and so on. And also, even if it's going to be, if the water is going to be released over 40 years, there will be more water that will be accumulating. That was also not really discussed in the RIA. So many more tanks will have to be built in the process. Bioremediation should be considered. So for example, plants, fungi, and animals can remove radionuclides from water and even from solid waste. This has not been explored to TEPCO in the official documents. Use of ALPS treated water for making concrete is one of the ideas that Dr. Makajani came up with for specific applications where there's little human contact. Cleaned tank water containing only tritium could be used to make concrete in locations that don't have much human contact, like bridges and so on. And the concrete would shield the tritium beta particles, even if it's crushed into rubble. And because of the 12-year half-life of tritium, it'll quickly decay. So it'll become basically harmless in a short while, as long as the tritium has been removed. The other idea is safe extended storage. Same idea, extend the storage, the tritium will safely decay over 12 years as long as all the other radionuclides have been in it, and then it can be safely released, and it won't do so much damage to, won't have such a burden. So I just want to conclude that this is an opportunity for Japan to lead and think differently about nuclear waste disposal, to implement safer and more sensible options. And that could open a door for others to move on from present dilution as a solution to pollution practices to more ecologically protected ones. So I think I'll leave it there.